Hello everyone, this is Professor Ng Chi Kun from Unimas. In this video, I'm going to give you a lecture on maximum inference line at a point due to a series of concentrated loads. So the maximum effect caused by a live concentrated force is determined by multiplying the peak ordinate of the inference line by the magnitude of the force, as we have seen in the previous lecture. In some cases, for example, wheel loadings, several concentrated loads must be placed on structure. Trial and error procedure can be used, or a method that is based on the change in function that takes place as the load is moved can be used. So there are two methods here. So first method is by trial and error, and then the second method is by looking at the change in function when the loads are moving. So let's look at an example here. So now we consider the simply supported beam with associated inference line for shear at point C, as we have seen in the previous lecture. We have already learned how to draw the inference line for shear at point C, like this. Okay, so now the maximum positive shear at C is to be determined due to the series of concentrated loads moving from right to left. So we are going to move this set of loads on the beam from the right hand side to the left hand side. Okay, and then critical loadings occur when one of the loads is placed just to the right of C. So the critical loading will occur when one of these point loads is placed just to the right hand side of C. Okay, so now we look at the first case. Okay, so case 1, the arrangement of load is like this. So one of the point loads, meaning that this 4.5 kilonewton load is just to the right of C, right? So meaning that this 4.5 kilonewton load has not moved past point C, is just about to pass point C. So it's just to the right of point C. And then the 18 kilonewton load is here, and then the other 80 kilonewton load is here. So we just determine the ordinates of each of these on the shear inference line, and then we multiply each of the load with each respective ordinate on the inference line, and we are going to get the total shear at point C, okay, due to the arrangement of load like this. Okay, and then case number 2, we'll be looking at when this 18 kilonewton force is just to the right of C, so it hasn't passed through C yet. Okay, it's just about to pass through C, and it's still on the right hand side of C here. Alright, so with this arrangement of load, we determine the ordinates on the inference line for each force. So for this 18 kilonewton force, the ordinate is 0.75, because this is on the right hand side of C. Alright, so we calculate the shear force due to all the three concentrated loads, and it gives us 24.19 kilonewton. Alright, and then case number 3 is when this 18 kilonewton force is just to the right of C. Okay, so in this case, this 4.5 kilonewton force is exactly on the support A. Okay, so the ordinate here is 0, the ordinate here is 0.125, and the ordinate here is 0.75, because it's just to the right of C. It hasn't passed through C yet, right? Okay, so we multiply each respective force to the respective ordinates on the inference line, and we are getting the effect of all these forces on the shear at point C. So for the third case, the shear force at C is 11.25 kilonewton. So we may conclude that from all the three cases, the maximum shear force is when the arrangement of load is like this, okay, when the middle 18 kilonewton force is just to the right of C, and this is the maximum shear force at point C due to the loading in case 2 like this, okay. So we can conclude that case 2 use the largest value for VC and therefore represents the critical loading. Investigation of case 3 is unnecessary since by inspection such an arrangement of loads would yield VC3 smaller than VC2. Trial and error can be tedious at times. So the critical position of the loads can be determined in a more direct manner by finding the change in shear. This is not the shear force, but it's the change in shear force. Okay. So which occurs when the loads are moved from case 1 to case 2 and then from case 2 to case 3. As long as the computed change in shear is positive, the new position will yield a larger shear. So this is obvious when the change in shear is positive, meaning that the shear force has increased. Okay, so the new position will yield a larger shear. Each movement is investigated until a negative change in shear is computed. So the change in shear from position 1 to 2 can be calculated by using the force multiplied by the change in shear. So the change in shear can be calculated using the slope of the function multiplied by the change in position. Okay, so and then if a load moves past a point where there is a discontinuity in the inference line, the change in shear will be directly the force multiplied by the jump. Okay, so in this particular shear force inference line here, we have a jump here. So the jump here is from 0.75 to minus 0.25. So the jump here is minus 1. Okay, so whenever the force moves past this discontinuity here, there's a jump of negative 1. Okay, so the use of above equation will be illustrated with reference to the beam, loading and inference line for VC as shown. So in this case, the forces or the concentrated loads are moving from right to left. Okay, so they'll be moving on a positive slope if we look at the movement of the loads. Technically speaking, this corresponds to negative slope, isn't it? Okay, in a function. But now the forces are moving from right to left. So the forces are moving on an increasing slope. Okay, so this slope is considered positive for this movement from right to left. Okay, same as on this portion of the function as well. Okay, the loads are moving from right to left, so they are moving on a positive slope also. Okay, so therefore we get a slope which is positive here. Okay, so the slope here and the slope here are the same. Okay, so the slope here is 0.75 over 12 minus 3 meter, which is this, and it should be similar to this as well. Okay, 0.25 over 3 is the same as 0.75 over 9 as well. Right? And then the jump at C is, technically speaking, should be minus 1. Okay, but the magnitude is 1. But in this case, it jumps down. So technically, we just take it as minus 1. Okay, although the magnitude clockwise is 1. Right? So now we look at what is the change in shear force from case 1 to case 2. Okay, so case 1 to case 2, it happens when this 4.5 kilonewton move to the left by 1.5 meters, right? So this force moved by 1 meter on the beam. Okay, so similarly, the 18 kilonewton force here and the other 18 kilonewton force here will move by 1.5 meter to the left also, right? So when this 4.5 meter is just to the right of point C here, and it moves here, it experiences a jump of -1, and then it moves out the slope again by 1.5 meter to the left, right? As we can see from here, right? So the change in shear force due to this movement from here to here is due to the 4.5 meter multiplied by the jump, okay, of -1, and then it moves out the slope, okay, by 1.5 meter in the horizontal direction to the left. So that will be given by the force multiplied by the slope multiplied by the total movement of 1.5 meter here, right? And then the second force that we look at is this 18 kilonewton force here. So this 18 kilonewton force here initially is here, and then it moves to this point here, okay, from case 1 to case 2. So in this case, this force moves on the slope by 1.5 meter in the horizontal direction, and there is an increase in shear force. So the increment is calculated based on the force times the change in the ordinates. Okay, the change in ordinates is given by the slope multiplied by the horizontal dimension, 1.5 meter. Okay, and then the next force that we look at is the 18 kilonewton force here. It moves from here to here. Okay, so meaning that it moves by 1.5 meters as well. Okay, so in this case, it moves from this ordinate to this ordinate. Okay, so in this case, the change in shear force will be given by 18 multiplied by the change in shear force here. Okay, so this is the force multiplied by the slope and then multiplied by the horizontal distance that the load has moved. Okay, so if we solve for this, then we're going to get a positive 0.563 kilonewton. So in this case, meaning that when the force or the system of forces here moves from this situation to this situation, there is an increase in shear force. Okay, so the increase in shear force is this much. So meaning that the shear force caused by this arrangement of load is higher than by this arrangement of load. Okay, and then next we will look at what happens when the system of loads have moved from case 2 to case 3. Okay, so in this case the 4.5 kilonewton moves by 1.5 meter. So the ordinate moves from minus 0.125 to 0. Okay, so the change is the force multiplied by the slope multiplied by the horizontal movement of the load. Okay, and then next we look at this 18 kilonewton force. This 18 kilonewton force initially is just to the right of point C. So when it moves past point C from here to here, so it experiences a jump down by -1. Okay, so therefore 18 multiplied by -1. Okay, and then the 18 kilonewton force move up on the slope, okay, by 1.5 meters to the left. Okay, so there's an increase in shear force on this slope. So 18 times the slope times the horizontal movement. And then this 18 kilonewton force move from here to just to the right of point C. So it's moving from here to here. Okay, so it moves up the slope. Okay, so the change is 18 times the slope times the horizontal distance that this force has moved from case 2 to case 3. So the total change in shear from this arrangement of load to this situation is negative 12.94 kilonewton. So in this case, it means that there is a decrease in shear force when we move this system of forces from this location to this location. So meaning that the shear force in this case is higher than in this case. So just now from case 1 to case 2 there's an increase. Okay, and then from case 2 to case 3 there's a decrease. So meaning that case 2 will produce the highest shear force in this case, okay, as what we have seen in the trial and error method as well. Alright, so next we want to look at moments. Okay, so for first you need to draw the bending moment inference line for point C. Okay, now we just want to look at point C. So we draw an inference line for MC. Okay, so the maximum ordinate is at 3 meters here, and then the value is 2.25. In fact, the unit is meter, okay, but we normally omit the units in inference line functions. Okay, so now you want to find out what is the maximum moment caused by this arrangement of load when it's moving from right to left on the beam. Okay, so similarly we look at the change in moment, okay, when this system of forces is moving from one location to the next location, and we take the force multiplied by the slope multiplied by the change in location of the force as the change in moment. Okay, so please take note that on this bending moment inference line there are two slopes. Okay, so here you have to be careful. So when the force is moving on this slope from right to left, there's an increase in moment. Okay, when the force is moving on this portion of the beam, moving from right to left, there's a decrease in moment. Okay, so we have to see whether the force is moving on this side of the beam or is moving on this side of the beam. Okay, and then you have to use the correct slope. Alright, so let's see what happens when we move from case 1 to case 2. Okay, so case 1 to case 2 meaning that the force of 9 kilonewton is just to the right of point C, and then it move past point C and then move to the left by 1.2 meters. Right? Okay, so in this case point C is supposed to be here. Okay, so in this case this diagram is not so correct. Okay, so bear with it. Okay, point C is supposed to be here. Alright, okay, so when the loads of case 1 are moved to case 2, it is observed that the 9 kilonewton force, okay, decreases delta M12, right? And then the 18 kilonewton and the 13 kilonewton forces cause an increase of delta M12. Okay, so it's obvious that when the 9 kilonewton force is moving to the right, it's moving from here to here. Okay, and then when this 18 kilonewton force is moving from here to here, it's moving from here to here, right? And then this 13 kilonewton force is moving from here to there. So there's an increase in moment, right? So meaning that delta M from case 1 to case 2 is this 9 kilonewton force multiplied by a slope on this side. Okay, so the slope on this side is considered negative because there's a decrease in moment when the load is moving from right to left. Okay, on this slope here. Okay, so this slope is considered negative. So the value is 2.25 over 2.25 over 3. Yeah? Okay, and then the movement of the force on the horizontal direction from right to left is 1.2 meters, right? And then for the 18 kilonewton force here, it also moves by 1.2 meters, but now it's on the positive slope. Okay, so this slope here is 2.25, okay, divided by 9. Okay, so 2.25 divided by 9 is the slope, because the force now move from right to left, so there's increase in moment, so we take this as positive slope. Okay, so the force is 18 times the slope times the movement distance of 1.2 meter, okay, from here to here. Okay, so this is the value, 18 times the slope times 1.2 meter. And then next we look at this 13.5 kilonewton force. So from here to here, it also moved by 1.2 meters. Okay, from here to here by 1.2 meter, and is on the positive slope. So 13.5 times the positive slope times the horizontal movement of 1.2 meters. So we get positive of the change in moment from case 1 to case 2. So meaning that case 2 will yield a higher bending moment than case 1 for MC, right? So this is only moment at point C. Okay, so next we want to examine what will happen when the loads are moved from case 2 to case 3. So from case 2 to case 3, okay, this 13.5 kilonewton force will move by 1.8 meter just to the right of C. Right? So meaning that all these forces will have to move to the left, okay, by 1.8 meters. Okay. So in this case, we look at each of the effect of each of the force. So let's look at the 9 kilonewton force first here. So this 9 kilonewton force moved by 1.8 meter to the left. So it moves from here to here. So it's moving on the negative slope. Okay, by 1.8 meters. Okay, so from here to here. Okay, so we take it as negative slope on this side. So 9 times the negative slope times the horizontal movement of 1.8 meter. Okay, and then secondly, we look at this 18 kilonewton force. It moves by 1.8 meters from point C here, just to the right of point C, to this location here. Okay, so mean that it's moving from here to here. Okay, by 1.8 meter from right to left. So it's moving on the negative slope. Okay, so the 18 kilonewton force also move on the negative slope multiplied by the horizontal movement. Okay, so that will give you the change in moment due to the 18 kilonewton force from right to left. And then for the 13 kilonewton force, is moving from here to here. So it's moving from here to here. So meaning that on the inference line is moving on the positive slope. Okay, so we have a positive slope here of 2.25 over 9. Okay, and then multiplied by the force magnitude multiplied by the movement of 1.8 meter. So when it moves by 1.8 meter, you notice that there's an increase of this much of value in the inference line. So that is given by this value here. Okay, the change in the ordinates of the inference line, and then multiplied by the force is becomes the change in moment. Right? So you see that the total change in moment due to the movement from here to here is negative 30.38 kilonewton meter. So meaning that the change in moment from case 2 to case 3 is negative. So meaning that case 2 use a higher bending moment at point C, right? So the greatest moment at C will occur when the beam is loaded as shown in case 2, right? Because from case 1 to case 2 there's an increase in moment, okay? And then from case 2 to case 3 there's a decrease in moment. So the maximum moment on point C is given by the load arrangement in case 2. So in case 2, the 9 kilonewton force is here, okay, with the ordinate of 1.35, okay, and then the 18 kilonewton force is at 3 meter here, and the ordinate on the inference line function is 2.25, and then the 13 kilonewton force is at 4.8 meters on the beam, okay, and then the ordinate is 1.8. Okay, so if we calculate the total moment, it's equals to 77.0 kilonewton meter. So this is the maximum moment at point C, okay, due to the moving load moving from right to left. Okay, so next we want to look at another example. So in this case, you are asked to determine the maximum positive shear created at point B in the beam due to the wheel loads of the moving truck. So this truck is moving from right to left on the beam. So now we want to check the maximum positive shear at point B. So in that case, we need to draw an inference line for shear at point B. Okay, so the inference line for shear at point B will look like this. Okay, either you use the qualitative method of drawing it and determine what are the key values, or by using tabulating value method, or by using writing the functions method. Okay, so now we want to study what is the effect of the 18 kilonewton load moving by 0.9 meter on the beam from right to left. Okay, so imagine that the 18 kilonewton load acts as to the right of point B, so that we obtain its maximum positive inference here. So meaning that the 18 kilonewton force is just to the right of this point B here. Okay, so it hasn't moved past the point yet, it's just to the right of point B. Okay, so beam segment BC is 3 meter long, so the 45 kilonewton load is not as yet on the beam. Okay, so imagine that this 18 kilonewton force is already here. Okay, and then it moves by 0.9 meter from here to here. Okay, so when the 18 kilonewton force is here, the 40.5 kilonewton force is here. Okay, and then the 67.5 kilonewton force is here. Okay, so when this 18 kilonewton force move by 0.9 meter, okay, so 18 kilonewton force will move from here to here, and then the 40.5 kilonewton force will move from here to just to the right of point B, and then the 67.5 kilonewton force will move from here to here by 0.9 meter, and you can see that this 45 kilonewton force is still not moving on to the beam, right? So this 45 kilonewton force is still outside of the beam, so the effect of shear is just caused by these three forces when the 18 kilonewton force has moved from right of point B by 0.9 meter to the left on the beam. Okay, so when the truck moves 0.9 meter to the left, the 18 kilonewton load jumps downward on the inference line by 1 unit. Okay, so there's a jump of 1 unit, but it's a negative jump. Okay, from here to here, right? From just to the right of point C to the just to the left of point C, there's a jump of -1. Okay, so although the 45 kilonewton load also moves forward 0.9 meter, it is still not on the beam, as I have explained just now. Okay, so the effect on change in shear force will just be caused by three concentrated loads. So the 45 kilonewton load has not moved on to the beam. Okay, so 18 kilonewton force move past point C from just to the right of C to just to the left of C will cause a jump of -1. So the change in shear will be 18 times -1. And then after that, the 18 kilonewton force move from here to here by 0.9 meter. Okay, so there is a change in shear, okay, which is an increase. Okay, so we take this as a positive load for the movement of load in this manner. Okay, so there is a positive shear change. Okay, so the slope is positive, right? 0.5 over 3. So it's 0.5 over 3, and on this side also is 0.5 over 3. Okay, that's the magnitude of these two slopes of the function. Alright, and then multiply by the horizontal movement of 0.9. Okay, so actually this term here, the slope multiplied by the horizontal distance, gives you the change in ordinates. Okay, so the change in ordinates multiplied by the force will give you the change in force, right? And then the 40.5 kilonewton load also move by 0.9 meter, and it's moving up the slope. Okay, so and then 67.5 kilonewton force also move up the slope by 0.9 meter horizontally, right? So the total change in shear is positive, right? So meaning that when the 18 kilonewton force move by 0.9 meter from just to the right of point C and is moving from right to left, it will cause a change in shear of positive value. Okay, so now we want to look at what happens when the 40.5 kilonewton load is moving to the left by 1.8 meter. Okay, so meaning that the 40.5 kilonewton force is just to the right of point C, and it moves to the left by 1.8 meters. Okay, so meaning that this 40.5 kilonewton will move by 1.8 meters. Okay, so this 18 kilonewton force is here, and it will move by 1.8 meter as well. Okay, and then this 67.5 kilonewton force will move by 1.8 meters as well. Okay, so when the 40.5 kilonewton is just here and it move across point C, there's a jump. Okay, so meaning that there's a jump of -1. Okay, so there's a jump of -1, right? And then the 18 kilonewton force, okay, move by 1.8 meters along the slope. Okay, and then the 40.5 kilonewton force experience a jump, and it moves on the positive slope of the inference line by 1.8 meters or so, same as for the 67.5 kilonewton force, right? And then down, the 45 kilonewton force will move by 1.2 meter when it's on the beam. Okay, so initially you can see that when the 40.5 kilonewton force move from just to the right of B to this position, okay, so when the 40.5 kilonewton force is here, this 45 kilonewton force is outside of the beam, right, at 0.6 meter there. Okay, 0.6 meter before it reach point C. Okay, when this 40.5 kilonewton moves from point B to this location here, this 45 kilonewton move from 0.6 to C, okay, and then another 1.2 meter on the beam. Okay, so I mean that this 45 kilonewton force moves by 1.2 meters, okay, from C to here, right? So meaning that the 45 kilonewton force due to the movement of 40.5 kilonewton force from B to here by 1.8 meter, this 45 kilonewton force moves on the beam by 1.2 meter. Okay, so the 45 kilonewton force moved by 1.2 meters along the beam, and then we multiply by the slope, we will get the change in shear force due to this 45 kilonewton force. So in this case, we still get positive change in shear force, right? And then next we want to see what happens, okay, when the 67.5 kilonewton force, okay, move by 1.8 meter. Okay, so in this case, what we want to see is that when this 67.5 kilonewton force move by 1.8 meter, so meaning that this 67.5 kilonewton force will move from here to here. Okay, so at the same time, this 40.5 kilonewton force will move from here to there, and then the 18 kilonewton force will move out of the beam also. Okay, so you can see that when 67.5 kilonewton force move from just to the right of B to here, okay, this 40.5 kilonewton force will move on the beam by 1.2 meter before it goes out of the beam, right? And then this 18 kilonewton force will move on the beam by 0.3 meter before it's out of the beam, right? And then this 45 kilonewton force will move from here to just to the right of point B, right? So in this case, the 67.5 kilonewton force will experience a jump of -1, okay? And then again, it moves on the positive slope by 0.5 over 3 times 1.8 meter, right? And then we look at what happens to the 18 kilonewton force, okay? So as I mentioned just now, the 18 kilonewton force will move out of the beam after moving 0.3 meter, okay, before it reaches the support A and then out of the beam. So it will only move on the inference line function by 0.3 meter before it reaches 0, okay. So meaning that the movement of the 18 kilonewton force is only 0.3 meter. Okay, although this 67.5 kilonewton force moved by 1.8 meter, this 18 kilonewton force will move on the beam by only 3 meter and then it's out of the beam already. No more inference. Okay, after moving 0.3 meter to the left. So meaning that the movement of the 18 kilonewton force is only 0.3 meter and then multiply by the slope of the function, we will get the change in the ordinate, and then the change in the ordinate multiplied by the force, we will get the change in shear force. Okay, and then the 40.5 kilonewton force, the 40.5 kilonewton force will move on the beam by only 1.2 meters, okay, and then it will be outside the beam already. Okay, so the total movement of the 40.5 kilonewton force is only 1.2 meter. Okay, so the movement of the force is only 1.2 meters, and then multiplied by the slope and then multiplied by the force itself, we get the change. Okay, and then for the 45 kilonewton force, it moves by 1.8 meters. Okay, it moves from here to here. Okay, so it moves from here to here on the positive slope. So the change in ordinate is the slope multiplied by 1.8 meter. Okay, so the slope multiplied by the horizontal movement multiplied by the 45 kilonewton force will give you the change in shear force due to this 45 kilonewton force. So we can see that due to the movement of 67.5 kilonewton force from just to the right of point B, and it moves to the left along the beam by 1.8 meters, okay, then we are getting a negative change in shear force. Alright, so I mean that by moving 67.5 kilonewton force to the left of the beam from point B, okay, the shear force becomes less. Okay, so in this case, the correct position of the loads occur when 67.5 kilonewton is just to the right of point B. Okay, so this will be the arrangement of load that will cause the maximum shear force at point B here. Okay, so the value will be just the force multiplied by the ordinate on the inference line function. Okay, so here we get 18 multiplied by minus 0.05 and then plus 40.5 times 0.2 negative, and then 67.5, because this force is just to the right of point B, so it's this ordinate. Okay, so 0.5 is the ordinate multiplied by 67.5, and then for 45 kilonewton is multiplied by 0.2. Okay, so we get 33.8 kilonewton. So this is the maximum shear force at B due to the system of forces moving from the right hand side of the beam towards the left hand side of the beam. Okay, so in practice we also have to consider motion of the truck from left to right and then choose the maximum value between these two situations. So what it means here is that you reverse the truck and then start moving the truck from the left hand side to the right hand side. Okay, if we consider that, okay, we consider the truck is moving from the left hand side to the right hand side, then all the load will move on a negative slope. Okay, so when the load moves, there is a negative change in shear force when the load moves from the left hand side to the right hand side. And then the jump, okay, the jump will be when the load is just to the left of point C and then it moves across C to just to the right of point C. So the jump will be positive 1 in this case. It jumps from negative 0.5 to zero point 0.5 when the load moves from left to right, okay, across the discontinuity, right? Okay, so that's all for this lecture. Thank you very much for listening.